Hello everyone, welcome to this video. For those who don't know me, my name is Purvi Arya and I am a student in IIPS DAVV Indore, enrolled in the class of Dr. Shaligram Prajapat on numerical analysis and design. In this video, we are going to go through the solutions of some questions that were assigned by our professor to test our knowledge. So let's begin. This is question 1, which says to write an algorithm to accomplish the task for polynomial in the given following table. The tasks are: first task to evaluate the polynomial with iterative approach and recursive approach. Second is to divide a polynomial by x minus r. And third is to find the derivative of the polynomial. The polynomial given here is an x to the power n plus an minus 1 x to the power n minus 1 plus an minus 2 x to the power n minus 2 plus an minus 3 x to the power n minus 3 and so on. It goes till a1x plus a0. So let's see first the evaluating the polynomial. First technique is brute force technique, that is the iterative approach. What we do here is we initialize the sum variable s to 0. For each term of the polynomial from highest to lowest degree, we compute the value of the term by multiplying the coefficient of x raised to degree of the term, and then we add the value to the sum, then return the value of s as value of the polynomial. Okay, first we take the value of x, n and a. That is, we initialize a, x and n. We take sum equal to 0. Then for I is we use a for loop here from 0 to n in steps of 1 to read a of I. That is, we find the value of a0, then a1, then a2. This we find it up to an. Okay, then we initialize another for loop, that is from n to 0 in steps of -1, that says that sum equal to sum plus a into I, a of I into x to the power I. Now the loop is from n to 0, that is, first we get the values of ai, that is a0, a1, a2, a3, and then we have to multiply it x to the power I. That is, if a0 we find, then it is a0 x to the power 0. Then if we find a1, then it is a1 x to the power 1. This says sum is equal to, now we started from the back, n to 0. Then this says that we find a n x to the power n. We add it to a n minus 1 x to the power n minus 1. Then we add this to a n minus 2 into x to the power n minus 2, and this thing goes on up to a1x plus a0. So this is our end sum. This is first way of iterative method. Now let's erase it. Let's move on to second method, that is recursive method. Recursive method and iterative method gives the same result, but the only difference here is we use function recursively. We create a function here, int polynomial, and we take values of int n, int x, and We take the values of n, x and a. Then if the polynomial p of x equal to 0, then we return as it is. Okay, then we return a of 0. Else, if it is not 0, then we return a of n into x to the power n plus the polynomial as it is. That is, we take a n x n plus a n x n minus 1 a n minus 1 into x n minus 1, and the same it goes to a a1x plus a0. It says that read x, n and a, we initialize sum to 0 as we did here. Then for loop I equal to 0 to n, we say a1, a2, a2 the value of here, then we end the polynomial. Let's see this algorithm for evaluating using recursion. If the degree of the polynomial is 0, return the value of the constant term a0. As we seen here, we have returned the value. Otherwise, compute the value of recursively by first computing the value of polynomial degree n minus 1 by calling the function recursively with the polynomial of degree n minus 1 as argument. Then computing the value of current term by multiplying the coefficient with x. See, if the current term here was a x minus 1. If the current term here was an, then we multiplied it with the coefficient of x, let's say an xn, then an minus 1 xn minus 1. Then we add the computed value to the polynomial degree n minus 1, then return the value of the polynomial. That is the same thing. Both gives the same result. And now let's move on to our part 2, that is divide a polynomial by x minus r. See, algorithm for dividing a polynomial p of x by x minus r. This is the algorithm. Okay, first we read the value x, n, a and r. Here we take r as the remainder. Then we initialize the sum equal to 0. For I equal to 0 to n, read a of I. We read the value a of I, that is a1, a0, a0, a1, a2, a3, and then end for we take the question and remainder 0. Let's first read it. Initialize, it says initialize the question polynomial and q and remainder r to 0. We have initialized it here, q and r to 0. For each term of the polynomial from highest to lowest degree, compute the value of current term of the question by dividing the coefficient by x minus r. It says the current term को हमको क्या करना है, divide करना है coefficient से x minus r से. See, current question, let's say ai is the number, then ai is the polynomial, we divide it by x minus r. Add the computed value to the quotient polynomial q. We added it as it is to quotient polynomial q. Compute the value of current term of remainder by multiplying the quotient of the current term. We multiplied with x minus r. See, quotient multiplied by x minus r. Subtract the computed value from the current term of the polynomial and then add the computed value to the remainder. We subtracted this value to the current term and then we added it to the remainder. Return the question and the remainder. Then the question and remainder are returned. We get q, comma, r. Now let's see another method, that is algorithm for computing the derivative of polynomial. This is derivative. It says to initialize the derivative of polynomial d to 0. Just a minute. We have initialized d to 0. Before that we have read the value of x, n and a. We have initialized the sum to 0, and then for I equal to 0 to n, that is, we have determined the steps. We have find out a0, a1, a2, a3 up to an, and then we have initialized derivative equal to 0. For each term of the polynomial from highest to lowest degree, compute the value of derivative of current term by multiplying the coefficient with the degree of the term and subtracting 1 from the degree. What they have done is they have multiplied it with the coefficient n minus 1 and then stored it to the current derivative. Add the computed value to the derivative. Then this computed value is added to the derivative d and then stored in d. This steps goes from n to 0. It goes from a n xn to a0, and then we write the value of d. So this is how first question's algorithm are solved. So let's move on to question number 2, which says to write an algorithm or flowchart of the following task and complete the table. So we are having given here two datas, data 1 and data 2. Inside this we are given n1, n2, two values, and we are given a task of subtraction, multiplication and division, and we have to write a flowchart of them. So let's begin with subtraction. Algorithm for subtraction. As here you can see, we start here. Just a second. We read the value of n1 and n2. Here n1 is divided into two parts, m1 and e1. m1 is the mantissa 1 and e1 is the exponent 1. Same goes for n2, mantissa 2 and exponent 2. First we check if exponents are equal or not. We check if e1 is equal to e2. If they both are equal, then we add m1 and m2 and store it in m, and for e we either take e1 or e2 because both of them are same. We move down there. We see if it is in a normalized form or not. If it is in a normalized form, then we print m and e and then we stop. If they are not in a normalized form, then we come down here. We normalize it by shifting the decimal part for 0 or 1. We normalize the value given here, and we normalize it by shifting the mantissa and adjusting the exponent. If the exponent is greater than 99, then we print overflow. If it is not greater than 99, we check if it is less than 99. If it is less than 99, then we print underflow. If both of this condition is false, then we print A. What is A here? A leads us back to this point. Now we check if when A brings it back to normalized, we check again if this is normalized or not. When it is normalized, we print it. If it is not, then again we follow the same procedure. Now let's check if e1 and e2 are not equal. We check then if e1 is greater than e2. If it is greater than e2, then we shift the mantissa of e2 by the difference of mod e1 minus e2. We take the difference of e1 minus e2 and shift the mantissa of e2 by that difference. And we add the mantissa 1 and mantissa 2 and store it in m. And here e1 is taken as e. Then we go to a. Here this a goes here, and then we check if it is normalized or not. If it is normalized, then we print m and e. If it is not normalized, we go here and follow these steps again. If e1 is not greater than e2, that is e1 is less than e2, then we shift the mantissa of e1 by the mod of e2 minus e1. And then we store m1 plus m2 in m, and here we take e2 as the e. Again we go to a here, and this step is followed again. Okay, this was the algorithm of subtraction. Now let's go to the algorithm of multiplication. Here we start. We read the values of n1 and n2 with mantissa and exponents. What we do here is m, we multiply m1 and e2, and we For E, we add E1 and E2. We check if this this thing is normalized or not. If it is normalized, then we print m comma e and then we stop here. If it is not normalized, then we normalize it by shifting the decimal part for 0 comma 1 and into, and for each shift of mantissa adjust the exponent. We have to normalize it by shifting the uh, ment- by shifting the decimal part, and if the exponent is greater than 99, we print overflow. If it is not, then we check if the exponent is less than 99. If it is less than 99, we print underflow. And if it is not, if both of them is not true, then we go to A. And A checks again for this normalization. So this process goes on again and again until the form is normalized or until it prints overflow or underflow. This was the algorithm for multiplication. Now let's check for the algorithm of division. We start here, we read the values of n1 and n2, and for here mantissa we divide m1 by m2, and for exponent we take the mod of e1 minus e2. Again here we see if it is normalized or not. If it is normalized, we print m and e. m is m is get by m1 divided by m2, and e we get by e1 minus e2, the mod. If it is not normalized, then we normalize it by shifting the decimal part of 0 and 1. For each shift of mantissa, adjust the exponent. Again, if exponent is greater than 99, we print overflow. If, if it is not greater than 99, but it is less than 99, we print underflow. And if both the conditions are false, then we go to A, and A takes us back to here, and then we check if it is normalized or not, and if it is, we print it. If it is not, we follow the same procedure again. So as you can see, for subtraction we get uh, for subtraction here the solution is underflow. Okay, it says it is underflow, and here there is no error, it gives the proper solution. For multiplication in these two values, the answer is overflow, and here there is no error. Error here is loss of itna 0974. In division n1 and n2, in both of the data we get overflow and underflow. So this was question number 2. In question number 3, we have to verify associative law and distributive law of arithmetic with fitting 4 mantissa digits and provide the correct answer if no number is truncated. We are given here two problems, and with a plus b minus c is not equal to a minus c plus b, we are given values of a, b and c. We have to check whether the question suits associative law and distributive law. So here a plus b minus c not equal to, we have to prove this. The given values of a is a equal to 0.5665 mantissa and exponent 1, b equal to 0.5556 mantissa and e equal exponent is minus 1, and c equal to 0.5644 mantissa where e is exponent is 1. So let's see LHS where a plus b. First we calculate a plus b. So the value of a is 0.5665, e equal to 1, and b is equal to 0.005556, where e is minus 1. What we do is we normalize the exponent of both of them because the exponents are not equal. So a plus b equal to, we add the mantissa of both of them, and then we get e as 1. Then we subtract c from it. So we get 0.572 e exponent 1 minus 0.5644 mantissa and exponent 1. When we subtract, we get 0.00761 exponent. Now let's solve RHS, that is a minus c plus b. When we subtract a from c, we get 0.0021 where exponent is 1, and b is equal to 0.5556 where exponent is minus 1. Both the exponents are not same. So we change the exponent of a minus c to normalize it, and then we get 0.2100 where exponent is minus 1. Then we solve both of them, a minus c plus b equal to, we get 0.7656 e minus 1, and here it was 0.7600, e was minus 1. Both of them are not same, so that proves that LHS is not equal to RHS. So in case 1, LHS was 0.0076 E1, RHS was 0.7656 E minus 1. Or after converting it or normalizing it, we get 0.7600 E minus 1. Clearly, A into B plus C was not equal to AB plus AC. So distributive law does not hold the same for this value, and it does not hold the same for associative law. Therefore, neither the associative law nor the distributive law holds this value. In case 2, to verify the associative and distributive law with fitting, we need to perform where LHS was this and RHS was this, which wasn't also the same. So this question does not hold the value for associative law and distributive law for both of the question, for 1 and for 2. Question number 4 is state true or false. First is minimize the number of arithmetic operation whenever possible. So there are several reasons why it is beneficial to minimize the number of arithmetic operation. But efficiency, accuracy, robustness, and memory usage. Overall, minimizing the number of arithmetic operation can lead to more of efficient, accurate, and robust algorithm with lower memory requirement. So this is the answer of this is true. Second is to avoid the difference of two nearly equal number whenever possible by alternate formulation of problem. If it cannot be avoided, then take the difference before doing other operation. This is also true because as you can see in example here, let's say A is 1.000001 and B is 0.0. C we have to calculate A minus B. In this case, the value of C is very small and may be lost due to limited precision because the number is very small after the decimal digit. It does not really matter. So to avoid this problem, it is recommended to use alternate formulation of the problem that avoids taking the difference of two nearly equal number. These two numbers are equal, therefore we have to avoid the difference of two nearly equal number. Therefore, this is true. Adding or subtracting numbers starting with the smallest number and works with numbers in ascending order. It is also true. Let's say A is 1.23, B is, all these are the number. If we add these number in descending order, we get the same answer. And if we add the number in ascending order, we get the same answer. So adding the small number first reduces the impact of rounding error and improves accuracy of the result. So it is true. Do not formulate an algorithm that tests whether a floating point number equals 0. So this is also true because it is not recommended to formulate the algorithm that tests whether a floating point number equals 0 because floating point numbers are not exact and their values may be subject to rounding errors. Conditioning of problems is normally due to improper formulation and can be eliminated by carefully reformulating the problem. A practical way it detected suspected ill conditioning is to alter the parameters by small amounts and observe their effect on the solution. So the answer of this is partially true because the conditioning of problem can be due to improper formulation, but it can also be due to nature of problem itself. Conditioning means that small changes in the input or parameters of the problem can lead to large change in the output or solution. This makes the problem difficult to solve accurately and can lead to numerical instability. Sixth question is, after a numerical algorithm is obtained, Check if it can lead to numerical instability. In such algorithms, errors grow in each step of the calculation. In such case, reformulate the solution procedure to get a stable numerical algorithm. It is also partially true because numerical algorithm can indeed lead to numerical instability where areas grow in each step of calculation. This can be due to a variety of factors such as ill conditioning problem, numerical round of error, and many more. To ensure numerical stability, it is important to carefully analyze the algorithm. Therefore, while checking the numerical instability, it is an important step in the development of numerical algorithm. Addressing instability may require a more thorough analysis. If severe rounding errors and consequent loss of significant digit is anticipated and no alternate formulation to avoid this is possible, then carry more significant digit in the critical calculation using floating point number in double precision mode. In this mode, the length of the mantissa is twice that the other floating point quantities. This is a true statement. One way to achieve this is by using the floating point number in double precision mode, which allows for twice the number of digits in mantissa compared to standard floating point. This can help to increase the precision of critical calculation and reduce the potential for rounding errors and affect the accuracy of the final result. It is important to note that increasing the precision of calculation can also increase the computational cost and memory requirements for the algorithm. Therefore, it is important to carefully balance the need for precision against the computational resources. Eighth question is, double precision requires large memory space and slow down calculation. It is true. Double precision requires more memory space than standard single precision, as each double precision floating point number requires 64 bits of memory compared to 32 bits for a single precision number. In third iteration of finding square root of phi with starting point 7 using Newton-Raphson method, relative error is 0.0013. Okay, so we have to solve this to test this. So based on the given information, we can take that square root of phi is x into n plus 1, that is 0.5 into xn plus phi upon xn, where xn in the nth approximation and xn plus 1 is the n plus 1th approximation. We can estimate the value of x3. Third iteration as follows. Here x0 equal to 7, x1 is equal to 0.5 into 7 plus 5 upon 7, and x2 is equal to 0.5 into 3 point the value of x1 plus 5 into the value of x1. So this is the formula of Newton-Raphson method. This is used to find out the values. Now assuming that relative error, so relative error we are given is 0.0013. So we put the relative error value to the given formula, and when we compare this to, we get the answer, that is, it is equal. Now, the iterative methods are compared on following parameters. The rate of convergence, the amount of computational efforts per iteration, and the sensitivity of methods to starting the value and intermediate value. It is also true because rate of convergence, it refers to how quickly the iterative method converges the desired solution. Amount of computational effort refers to amount of computational required to obtain the next approximation in the iterative process. And the third is sensitivity of the method to starting value and intermediate values. This refers to how the sensitive the method is to initial guess and intermediate values used in iterative process. So this is also true.